All right, everyone, welcome back. Let's talk a little bit more. I'd like to talk about one and two-dimensional motion, oftentimes projectile motion, but one and two-dimensional motion, generally speaking, and we'll look at a couple problems related to that, and some trigonometric considerations as well. So one and two-dimensional motion and some trigonometric considerations. I am going to be looking at three problems from the Serway and Buell book called College Physics, Volume 1, 11th edition. The problems will be, the first problem will be from the first topic in the Serway and Buell book. Hereafter, let's call it the Serway book, the 11th edition Serway and Buell book, College Physics, Volume 1, 11th edition. Just call it the Serway book. In the Serway book, chapters are called topics. So there's topics 1, 2, and 3, about which we will speak some today. From topic 1 on page 27, problem 45, for the first problem to be considered. For the second problem to be considered, from topic 2, page 56, problem 47 will be considered. For the third problem, from topic 3, from page 75, problem 13 will be considered. Should be pretty straightforward. A look at some of these problems. I may talk a little bit more than what the standard answer might be in at least one of these problems, in particular the first problem. Those of you who have me in non-calculus-based Newtonian physics know that we're using the Serway and Buell book, College Physics, Volume 1, 11th edition, the Serway book, as we say. So we're using that for those of you who already have me in non-calculus-based physics know that. Those who have me in calculus-based physics, or anybody else watching this, just know this is the book that we're considering. I'll read off the problems, and it should be pretty straightforward. You obviously have the feature that you can go back with the film and listen to what I had said. You can kind of go about it that way. There are numerous options to purchase books. If you've purchased a calculus-based book and it's from the same publisher, there are options where you can also purchase another book associated, or at least have access to another book associated with the same publisher, and there are deals with that. I have nothing to do with that. I do not work for any publisher. I'm just saying that as a matter of fact. Simple as that. I have no financial interest whatsoever in any of this process, and I don't work for anybody else other than the great university for whom I work, for which I work. Okay. So, but anyway, that's what we're going to cover. I'll be erasing some of this and actually get down to doing that. For the first problem, it will be from topic 1, page 27, problem 45. Let me read it to you. Let me write it down also as well. Let me answer the question. Let's talk a bit more about that problem more than what's even being asked of us. I think it's important to be able to do that. Okay. Let's take this down at this point, and let's just let's go for what we're going to do. Let's make sure I'm going to remember what it is I'm going to do on this stuff, you guys, as well. So, topics 1, 2, and 3. Problems 45, 47, and 13, respectively, from topics 1, 2, and 3. Okay, guys, let's take a look at some things and see how we can proceed on this. From topic 1, from topic 1 from the Serway book, problem 45. They're showing a particular triangle, assumed to be a right triangle, and so we'll say topic 1, problem 45, and we'll probably do a little bit of extra in addition to what they're asking us to do on this. So this problem 1 is not any problem 1 written formally as problem 1 in the book. It's me calling this problem 1 when the actual problem in the book in topic 1 is problem 45. But this is the first problem that I'm going to consider, and it's problem number 45 from topic 1. So you're looking at, now this is really not necessarily drawn to any great scale, you guys, but we're talking about a right triangle. They don't really label it as a right triangle, but we make the assumption indeed that it is. That's the assumption. And this is theta. This is phi. They're telling us this is 9 meters. They're telling us this is 6 meters. And they're asking a number of things. For that triangle right there, you guys, for that triangle right there shown in that figure that I've just drawn, what are A, the length of the unknown side, B, the tangent of theta, and C, the sine of phi? So, there's a lot going on here. I mean, I could just place this. I have this in my notes. I'll probably follow my notes pretty closely. I may not. My notes have it somewhat there. Those who have me as a teacher know that in Canvas I have the answers to all of these, and there may be film of this somewhere as well. It's hard to say. Sometimes I have no problem doing a problem over and having it stand alone or close to alone with just a couple other problems like we're doing right now. Maybe that's not a bad way to go. We know a bunch of things. The hypotenuse squared equal the hypotenuse C, the longest side squared, which would be 9 in this case. The hypotenuse squared is equal to the sum of the square of the legs. So we have this right here. Way I had written it is a little different. I mean, it doesn't matter. At this, basically, the argument is this. The hypotenuse squared equals the sum of the squares of the legs. You square each leg, do the sum of the squares of the legs, and you'll get the hypotenuse squared. C squared equals A squared plus B squared. R is what I called C. X is what I called the unknown side. We can call it X. And Y is what we called one of the known sides. So we have this. To make a long story short, let's solve for X. Subtract Y squared on each side. X squared equals R squared minus Y squared. Square root each side. And you got this. You got that. Well, that's as simple as that. Is how it's going to go, guys. You can basically, I'm just following my notes here. I'm trying to keep some consistency with it. If those of you who aren't going to see these notes, if you're not in my class, it doesn't matter which way you're going to look at it. Make sure you are exploiting the reality, the truth of the Pythagorean theorem in regard to mathematics, the mathematical reality of the Pythagorean theorem. So use that as you wish. If this is X, this is C or R, in this case we used it, and this guy was your Y. And you try to find out, so you got this song and dance right here, guys. At that point, do the mathematics, get to here. R squared is 9 squared. Y squared is 6 squared. 81 minus 36 81 minus 36 is 45. I mean, there's a bunch of ways you can play this, guys. How good's your math, right? The square root of 45 is the square root of the product 9 times 5, which is the square root of 9 times the square root of 5, which is equal to 3 times the square root of 5. That's probably the strictest mathematical way to write that. If you actually grind that out, you get that x is approximately equal to, sometimes they write this, they write like squiggly line like this, meaning approximately equal to or close to equal to 6.71. Watch out. With the calculators, you want to probably stay as accurate as possible when you're doing a whole bunch of operations, one after the other. Probably keep a very high degree of accuracy, a very high degree of decimal place accounting. Make sure there's a lot of decimal places taken into account. We'll get right here. This is x. That answers the question for A. What's the length of the unknown side? At this point, you guys, it's pretty straightforward stuff. I mean, for B, they are asking you for the tangent of theta. The tangent of theta is the rise over the run if you tilt the triangle in the right way, whatever that may happen to be. The tangent of theta is the opposite over the adjacent. The tangent of theta is the opposite over the adjacent. That's 6. This right here is 6.71. And so you got 6 over 6.71, or at least close to that. Remember, the most accurate one is this guy. But this is okay, but keep a large degree of accuracy so you still stay within the margins of error depending upon what you're being asked. The tan of theta, is 0.8944. Simple as that. So that's B. That's the end of the story as far as B is concerned. You know, you wish they would have asked you another question as well. By the way, what is theta? Well, heck, I can find what nobody asked me, but I could find what theta is at this point by saying theta based on other things that I have said, both in person with my classes and in other videos for that matter. If you want to find theta, and they already gave you what the tan of theta is, if you know the tan of theta is this, then theta would be the inverse tangent of the tangent of theta. Well, the tangent of theta is this. Nobody asked you this, but like I said, for a little bit of extra, this is a good thing to look at. What would be, by the way, what is that angle theta? I wish they would have asked us this. I'm going to do it anyway. We're going to do it anyway because we find it pretty of interest, pretty important to do. So the inverse tangent of 0.89, and again, we didn't, you know, I didn't in the actual notes. Don't go real far with this, but let's do it now. Inverse tangent, make sure you get your answer in degrees. Make sure your calculator's set to the right place. If you want radians, make sure it's set to radians. If you want to work with radians, make sure you're set to radians. If you want degrees or want to work with degrees, make sure your calculator is set to degrees. That's your responsibility. This is 41.809. For our purposes right now, let me not take it much further, but usually when you're doing problems, take it pretty far out. If there's like 8 more decimal places, write them down. Or at least have it in your calculator when you're doing a lot of this work. Take this stuff as far out as you can. Those who have me as a teacher know that your precision oftentimes is going to hinge on that you're not rounding off answers as you're going along. If you're rounding off answers as you're going along, you're asking for trouble. And that's the student's responsibility to make sure they don't get into that kind of trouble. As I said, take this stuff as far out as you can. You're allowed a 2% error when you're doing WebAssign work. But, you know, for now, let's have this under control. Okay, so we got this. Nobody asked, but we gave it. They asked for this. Same thing over here with the C. They're asking, well, heck, we can kind of cut to the chase on this one. I'll say a bunch of things here. Guys, just for the record, I mean, as I said, nobody asked, and we got to what we got. This is about 6.71. 6.71, and we did the whole jazz here. What does that mean? That means if you take this leg, if you take the length of this leg, which is this, and square it, and take the length, take the length of this leg, which is that, and square it. Take the length of that leg, which is this, and square it. Add the squares together, you're going to get what 9 squared is. This squared plus this squared is going to give you what that is squared. And that's we use the Pythagorean theorem to get that. Just for the record, just to kind of look at the consistency and the power of the mathematics, we did something extra here. We found the tan of theta. We found the tangent of theta right here, and theta was 41.8. Okay. Tell you what, we're assuming that's a 90-degree angle. This is 41.8 degrees. 90 degrees and 41.8 degrees is 131.8 degrees. How many more degrees would be needed for phi to be, for it to be 180 degrees with the sum of all 3 angles? You have to remember, the sum of all the angles of any triangle, and I've got that proved elsewhere in some aspects where I talk about the Pythagorean theorem and looking at least some sort of gut feeling proofs as to why the Pythagorean theorem is what it is, a proof looking at that, and then looking at how is it that any triangle has 180 degrees in it. Any triangle has 180 degrees in it, no more, no less. Exactly 180 degrees in it, no matter what kind of triangle it is. Then we talk about similarity of triangles and other things of that nature, and again, the Pythagorean theorem. So there's some gut feeling proofs as to why this is true. Over a couple of videos, I talk about that. We talk about similar triangles and the Pythagorean theorem and things like that, and they're labeled as such. And so that's available to you. I'm sure it's available in other resources as well. So that's at the discretion of the student if they want to look at some of that stuff. But I can see that this is a right triangle. This is 90 degrees. This is 41.8 degrees. If I add 90 degrees and 41.8 degrees, I get 131.8 degrees. That is going to be 48.2 degrees needed for everybody to add up to. Let me just see here. Right. Correct. 48.2 degrees is what phi would have to be. Nobody was asking us for any of these angles. For the record, if this is 90 degrees and this is 41.8 degrees, you would have to add 48.2 degrees in order for all 3 of these angles, this angle, and that angle, to add up to 180 degrees. So we already know that. We can kind of put that over to the side. It should round off to that. Well, actually, let's at the risk of even coming across as a little bit arrogant, let's just say, yeah, we already know we're going to arrive at this. Let me work with the sine function and figure out what's going on. They want to know, they're asking to find out what is the sine of phi. And we can take it from there. So for the sine of phi, you're talking about, now we're pretending we don't know this. We deduce this as I've shown you how we've deduced this. But let's pretend we don't know it. But we know how we can deduce this. We know that. What is the sine of phi? It is the opposite over the hypotenuse, which is 6.71 over 9. There's your sine of phi. (6.71 over 9). The sine of phi is opposite over hypotenuse. It's 6.71 over 9. And the way it is. I mean, so let's see what we got here. We got this. At the end of the day, what are we going to get? Okay, well, let's get some kind of approximation. These tend to be irrational numbers going on forever, depending to what degree of precision you want to go with or you're allowed to go with. Again, tend to err on the side of caution. I would advise going even further than this if you're given an answer on an exam, just to make sure WebAssign doesn't do something to you, okay? The precision that they want is 2% error tolerance, so watch out. 0.7456. There's your sine of phi for you. Okay, that's all they were asking. For the record, can we get this guy? Can we get phi? Sure we can. Phi is going to be the inverse sine of the sine of phi. The sine of phi is this, or at least approximately this. I'm confident it's going to hit right around here. So see if we have that under control. See if we're right. So sine inverse again, make sure the calculator is associated with the right units, always. In particular with angles, it can be a problem. It's 48.2106, good enough for me. At least for the aspect of the discussion that we're trying to talk about, trying to manifest here. There it is. So, I mean, that's the way it goes. If you don't, I mean, there's a whole lot can be said here. There's the Pythagorean theorem, there's the law. I mean, different things get said in different formulas out there. I don't know how many I want to actually throw at you when we're doing this, but I can just hit a couple things while we're at this. All right, so that will be what you need. Let me kind of give you a little bit of room to look at it as well. Okay. So, having said that, are there other things that can be said here, I guess you could say? Well, you know, there's a lot that can be said, and, you know, to what degree I want to talk about it within the context of what I'm trying to do in this particular video. I can say a few things, and you can look a little bit further, or we can talk about it in person, or it's in other places. I mean, this stuff gets discussed in other places. But there are mathematical proofs as to why this is true. Some pretty beautiful mathematics proving that this is true for a right triangle. If it's not a right triangle, there's this thing called the law of cosines. I don't know how often you see this. That's if a triangle's looking something like this, let's say. So you had something like that, which is clearly not a right triangle. If this was your theta, and this was your C, and this was your A, and this was your B, and let's say they're different length sides. When you're doing this, it almost looks like they're isosceles. But let's say they weren't. You could have something like this that works, and it's called the law of cosines. That can be proved with the Pythagorean theorem. There's also generally, again, for any kind of look to I almost wish I would have used this one for that one. I can just make this a little different. It doesn't matter. What I just said here was right, guys. It's not an issue. But let me just kind of just a little, here's A, here's B, here's theta, opposite the long side, call it C, and you can play the game like this. Let's say, there's a whole bunch of things you could say here. Let's say this is length C, small c, this is length small a, this is length small b, and let's say this big angle right here is capital C. And this length, so the angle opposite C, the angle opposite C is capital C. The angle opposite A, small a, is capital A. And the angle opposite B is capital B. And it doesn't matter what the triangle looks like. You basically have sine A over small a equals sine B over small b equals sine C over small c, called the law of sines. So there's things you can do to find sides, to find angles. So much of what goes on in basic vector analysis is we've said this before, those who've had me as a teacher know this before, vectors don't add like money, they add like triangles. You have to be able to resolve vectors from some kind of master triangle and add all the components of master triangles to get one huge triangle at the end. But everything adds in terms of triangles, which means what? We've got to know trigonometry. In any physics course that you take, even a basic physics course that's non-calculus based, you must know algebra well. And you must have some decent knowledge of trigonometry to succeed. And once you have a very strong basis in algebra and a decent basis in trigonometry, the physics itself becomes something that's very manageable. If you don't have the basic mathematics, it becomes very, very difficult. So make sure that you always have that basic mathematics. That's for sure. So law of sines for that. Okay, so there's something we could have said there for that particular problem, and we've done just that. All right, let's go to problem 2 and kind of take it from there. Or at least the problem 2 that I said we're going to call problem 2. So let me get rid of this. And for the second problem, we were looking at problem number 47 from topic 2. So let's get over there. Let's read that. I think within the context of doing the problem, you'll get an idea of what I'm trying to say regarding what's happening with that. So let us go through this. Excuse me. So let's go to the second problem that I thought is of interest in looking at some of this stuff. And I'm going to need to get a hold of a little more chalk, guys. Let me just see here what I got. Should be okay for a little bit. Okay. So So the problem 2 from topic 2 will be problem number 47. So okay, it's a neat problem, a neat kind of sort of kind of an aptitude type problem. Be a great problem to ask on some high stakes exam, where if you're told some information, can you think it out? Or if you got some basic information under your belt, can you think this thing out? It's not excessively conceptually a difficult question to be answering, but yet it gets you thinking. It's a kind of question that many people might have a hard time answering, even though it's very straightforward like this. It's a classic SAT type problem or GRE type problem or some sort of high stakes test type problem. You can almost visualize it being that way if the assumption was made that you had some physics background or they told you some within the problem itself. Well, I mean, let's talk about it. So, without further ado, I'm making the claim about the problem. Let me tell you what it is. So, for 2, in topic 2, problem 47. And let's get a look at what they're saying. Let me say it. So at least you have it in your background of this, guys. Obviously, the best way to do this is to have the book in front of you. That's not always going to be something possible, guys. Oftentimes, there's so many different ways to look at these problems as well. I'm at least going to show you one way. That doesn't necessarily mean that may be the only way. Maybe the most convenient way. It may not even be but it may not even be the best way. I believe that's a good way for it to be understood. Let me just make sure we are in agreement here, at least on the problem itself, and how many of these there are. So they ask a good amount of stuff here. Not bad. Okay, so here we go. It is on page, it is in the Serway book, the Serway and Buell book. It's in the Serway book, page 57, topic 2. It's problem number 47. A certain freely falling object released from rest requires 1.50 seconds to travel the last 30 meters before it hits the ground. A, find the velocity of the object when it is 30 meters above the ground. B, find the total distance the object travels during the fall. Here's, there's a lot contained within that brief problem. So let's kind of look at it. Let's just read it again. A certain freely falling object. A certain freely falling object. The object is held somewhere high up in the air, so to speak. It is held there. It's not thrown upward and it's not thrown downward. It is simply held at a particular height above the air, and we don't know what that height is. We do know that after the object has fallen a certain distance, it will be 30 meters away from the ground. After it has fallen a certain distance, it will be 30 meters above the ground. When it is 30 meters above the ground, it'll take another 1.5 seconds before it hits the ground. When it finally gets 30 meters above the ground, it's traveling so fast, whatever that may be, whatever that speed may be, it's traveling so fast right at the 30-meter mark that at the end of all the accelerating that's going to keep happening until it actually hits the ground at the very last instant, it's going to take 1.5 seconds to travel the last 30 meters before it hit the ground. You don't know how high this object was above the ground when they released it. They want you to find the velocity of the object when it hits, forgive me, they want you to find the velocity of the object when it is 30 meters above the ground. Find the total distance the object travels during the fall. And there's other things we could answer if we chose to do so, just for the sake of the mental gymnastics that takes place. That's good for us. There are a number of ways to get out of this. Probably the easiest is, you're saying somewhere high up in the air, there's a ledge, and somebody drops this thing from rest, and I mean complete rest, the real initial velocity is 0 in terms of magnitude. It is going to drop an entire distance. I mean, let me just kind of use the same notation in this problem. It doesn't matter what notation you use. It's going to drop an entire big distance of d. By the way, at a 30-meter height, and this is not drawn to any kind of scale. I don't know what's going on, guys, until the end. The drawing's just a guide. You know that. Anybody who's taken geometry at any level will tell you a lot of times don't base things on a drawing. The drawing is a guide just to give you some kind of guidance to how to look at the problem and visualize it. It's not in and of itself exact measurements by which you're going to draw good conclusions. It's just a guide. Well, the whole fall is d, and you're coming from a real dead stop, you know, when you're doing this. I don't want to put a symbol on this for a reason. I'll just say that initially, way initially, it's 0. When it's down here, you know, when it's here, you know, here it may be going 0, but here it's really moving, or really moving relatively fast. Down here, right before it hits, it's going even faster. Why? Because it keeps accelerating until the end. We're assuming that there's no deceleration associated with air resistance. There's no air resistance for our purposes. Okay. So the real big picture, you guys, you know, this right here is, you know, the real big picture. As we've said, I've drawn it twice, not just different colors on it now, right? But the real big picture is this, and this is another dynamic. And this is kind of where they're asking us to kind of play a game. In the end, we're going to find what this is. Okay, the big picture. So, there's uniform acceleration going on, guys. We know that any sort of distance traveled, any sort of distance y traveled or d traveled, we'll just call this distance y right here. This 30 we'll call y. It's the magnitude of the average velocity times the time it takes to get down there, which is equal to vi plus vf. Now the vi ain't the vi up here. The vi up here is 0. I'm talking about the vi right here. We'll talk about this guy having a vi associated with it, and we're talking about this guy having a vf associated with it. Well, wait a minute. There's some other stuff down the road. We know that vf is vi plus at. Now, everybody is falling downward. Those who have had me before or have seen other work that I have done, either on the internet or, like I said, in person, or just in other classes with other people, they'll tell you, if everything's falling down, there's really no, I could say contradiction, or there's really no fight between an upward and a downward. If everything's falling down, you might as well call it downward positive. And there's nothing to really worry about in that regard. So you can just say, if everybody's falling downward, we'll call G positive, as you saw me do in the past, and we're getting this. We can get something like this. Well, I'd like to look at that, because this right here, the average is the average of these two times time. And that's for the y, and that's for this guy. We're talking about this guy being the y, and D being the big one, let's say. Let's talk. Look at it. I don't know what VI is. This is a crazy VI. It ain't the VI of up here. The VI of up here is 0. That's easy. By the time it gets down here, it's moving fast, and that's going to be my new VI. And down here, it's going even faster because it's got gravity working on it all that time. It's still falling an additional 30 meters. So it's going to gain even more speed. VI is this guy. VI is this guy. VF is VI plus GT. You got this right here. And you got that. Okay, let's see what happens. Wheel and deal with the mathematics a little bit. VI and VI. VI and VI is 2VI. This is GT. So what we get is Y is equal to VI plus VI is 2VI plus GT, everything divided by 2. So let me actually go slow. I think you guys know what I want to do, and I tell you what, let's just write an extra line here and just do what we have to do. Tinker with this a little bit, and you can say a lot of stuff. In my notes, I write it slightly differently, but it is identical. I mean, do division here. If there's addition and or subtraction going on, you will distribute the multiplication and division. If there is addition and or subtraction present, and you are multiplying or dividing that quantity, you will distribute the multiplication or division. In plain English, the 2 goes into here, VI times, the 2 goes into here, 1/2 GT. So you got VI plus 1/2 GT times T. You're saying, okay, what's going on? What is he doing? How can we do this? There are a number of ways to do this without having to resort to the Pythagorean theorem. Forgive me, not the Pythagorean theorem, the quadratic formula. We don't even have to go there. There's so much given to us right up front. What do we mean? Well, y is equal to 30. VI is what we're trying to find out. That's its speed. That is the speed falling downward right at the location of 30 meters above the ground. VI is the speed at 30 meters above the ground. 1/2 GT is 1/2 times 9.8 times 1.5. That whole thing times 1.5. They told us it's 1.5 seconds. You guys, in the problem, they told us the fall from a 30-meter height is 1.5 seconds. Okay, guys, I should have more chalk. I think we got enough in front of us, guys. There's a lot here. It's its own mess, that's for sure. But you got all this. You got this. It's pretty good to me. Let's go. Let's see what we can do. Let's do some math on it. I'm going a little bit slower than I just want to make sure everybody's with me. So just forgive me if it's a little on the slower side here. This is VI. Still don't know what it is. 1/2 of 9.8 is 4.9. 4.9 times 1.5, right? Should be 7 point, trying to think what it would be. Let's see what we had here, man. I think I'd gone straight through it, so let me see if I can do this in my head, guys, without taking too much time here. I drew conclusions otherwise, but let's see what we got here. We have 1/2 times 9.8 times 1.5. Okay. 1/2 of 9.8 is 4.9. 4.9 times 1.5. It would be 7.5 if it was just a 5 times 1.5, not a 4.9. So 0.1 would be 0.15 less than that. I think you should be getting somewhere in the ballpark of 7.5 1.35 here times 1.5, you got the 30 here, and there's a number of ways we could go here, guys. I could, you could, probably the faster way to go, honestly, is take the 1.5, divide by 1.5 on each side. Divide by 1.5 over here, divide by 1.5 over here, and get 20, and then get VI equals 20 equals VI plus 7.35. That would be 12.65 for an answer for that. So kind of interesting how that plays out. You could, like I said, let me just do this really quickly. When you got to here and you're doing some of the mumbo jumbo I just did, you've got, and again, with the calculator, you don't need to be playing this sort of mental gymnastics all the time. You got it to here. Why don't you just go right to the finish of this thing? Divide by 1.5 here, divide by 1.5 here. This right here is 20. This goes, you got VI is equal to you got 20 equals VI plus 7.35. Subtract 7.35 on each side. Subtract 7.35 on each side, you get 12.65. That's how fast it's going, ladies and gentlemen. That's how fast it's going. That's how fast it's going at the 30-meter height. True. And again, you could, with the gymnastics involved here, it's just a lot lengthier process. You could go this times this, and that's kind of its own dynamic, how it all plays out. But I don't even know how. Let me just see actually how I did solve that. So you kick this around, right, and you do the mathematics here. You're going to get 11.025, and let me kind of leave it at that, guys, if you don't mind. I mean, you can go right here. You can look at this right here and subtract 11.025 on each side, and you end up getting 18.975 equals 1.5 VI. Divide by 1.5 on each side, and it's not going to be any kind of great surprise. We already just gave that answer in I could say a much simpler manner. You're going to get the same answer. You're going to get that. So that is the, what was the question on here, guys? And we can take it a little bit further. They are asking, find the velocity of the object when it is. So what are they saying here? Well, everything I've just said, given everything that I just said, they are asking, A, find the velocity of the object when it is 30 meters above the ground. That's the new VI, and we found that to be 12.65 meters per second. For the record, okay, that's it. I mean, that's the end of the story on that, guys. So what we can say with this, we got that for A. I mean, there's a lot can be asked here. We can just for the standpoint of practice and being strong with this stuff. Okay, so nobody asked this. I mean, this was A. I mean, if you're writing it way over here, then look at that's where the A should be. But here's A. Doesn't look where part A would be, but here is part A. Okay, so that's the answer. They're asking for that, and we write that down. In fact, let's put it in a more chronological fashion, I guess, or a more, put it in some kind of order that we're used to seeing things. We'll put this at the very top. Okay, so we got this. Nobody asked you for this. But how fast is that thing going at the very bottom? How fast it's going at the very bottom is VI plus AT, or GT. VF is equal to 12.65 meters per second plus 9.8 meters per second times 1.5 seconds. My S's and 5s look a lot alike, guys. I don't know what I'm going to do here, but okay, let's try to make it kind of small. Maybe look at it. But you got 12.65 plus 9.8. You got 12.65 plus the product, 9.8 times 1.5. Well, 1.5 times 9.8 is 14.7. So that's it. Yeah, that's exactly what it is. I mean, so if you take 9.8 and multiply it by 1.5, you get 14.7. 14.7 plus 12.65 is 27.35. Nobody asked, but they could ask you. Okay. So we know that. It's good. It's not bad to look at it. We could say a whole lot. Trying to think what they're trying to ask here. I'd like to ask. So, I'd like to ask a few more questions, more than they're asking, and try to answer those few more questions as well. Find the total distance the object travels during the fall. I recall, I don't know, you could say a bunch of stuff on this one, but let's pull everything out that we know. I mean, we got all this stuff written down here, guys. I don't know where. Let me stop. Let me stay here. Let me try to keep some stuff up here, I guess, as we do this. And you can always go backward with video to look a little more if you need to. I got an idea here. It's probably pretty easy to look at, to be honest with you. Is it true that any total distance fall from a height h or from a height d, let's use d, is you could say V, and this is useful. I mean, so it's good that we actually got this VF. This is at the very, very bottom, right before it hits the ground. VF over VI squared over 2A. Since everybody's falling down, that ain't going to be an issue. We're just going to treat everybody as though they're positive. There's no contradiction in any kind of directions going on here. That does happen if you fire a projectile and it's going up and it comes down, and there you better strictly enforce that G is indeed a positive number, and it's going to, but you're always using negative G. You're always using the fact that the acceleration is of a negative nature if there's something going up and then coming back down. And we've talked about that. So this is it. I mean, this will get us there to answer B. D is the total fall. What's the speed at the bottom? 27.35 squared. What's the initial? I don't mean this initial velocity. If I use this initial velocity, you know what I would get for a D? If I use the initial velocity of 12.65, I'd get 30 meters. That's the distance it traveled in 1.5 seconds. If it started one way, started the other, how far did it fall? If I put the 12.65 right here, squared it, and divided by 2G, divided by the product 2G, and this was 12.65, the quantity squared, it would spit out 30 as an answer, because that's what took place here. This would be 12.65 meters per second. This would be 27.35 meters per second. Do the math, do everything, and it would spit out 30. It would confirm it. That's that's fascinating in its own right. Well, why don't we do the same logic and know that the bottom is indeed 27.35 meters per second, and the top is 0 meters per second. So there it is. There it is. And let's do the math. You're going to do this whole thing. There is, and we'll talk. We got more we can say, I guess you could say. But I'm looking at this. Let me just make sure that I'm agreeing with myself, so to speak. Looking good. This thing, again, I didn't draw out the scale, but the total amount of height before the big fall down happened there you go. There you go. Could you pull this off? Well, okay, yeah, it works. It works. For the record, and there's a number of things that can be done. I don't know if I'm going to do every one of those, but at least if I give you a decent experience on this, I hope. The other ones are you can manifest those as well. You could say a lot. I mean, this is B. And we're done. I mean, this is essentially what they were asking of us. This is what they were asking of us, guys, to actually do. Now, you guys have all this. Let me erase a good part of this and this is basically the end of the story. That's all they were asking, and we already gave a little bit of extra work on the topic. But let's talk about something. Could you have, it'd be nice to know what the total flight time was. We knew that the flight time from 30 meters above the ground to the actual ground, from 30 meters above the ground to the ground, that 30-second fall, that 30-meter fall, okay, let me start over, forgive me, guys. We know that there is a flight time associated with the object falling from a 30-meter height if it's already moving. It fell from a height that was taller than 30 meters. It fell from a height, at the end of the day, we found out that it fell from a height of 38.16 meters. We know that if it falls 30 meters, but it's already been moving when it's at the 30-meter height, when it's already moving at that 30-meter height, as we now know, having started 8.16 meters above that 30-meter mark above the ground, having started 38.16 meters above the ground, when it gets to the 30-meter above the ground mark, it's already moving, and at that 30-meter mark, it'll take 1.5 seconds to hit the ground. That means there was a little bit of time before that. What is that total flight time? And you could do that a couple of ways. You could say, nobody went there. I mean, from what I'll look at it again. I don't think they even asked us that, but that doesn't matter. Who cares? It's a useful question to answer. Do we know that the total fall down, D, happens with a final speed, which is really fast, and we found that out to be 27.35, and a real initial, the true initial speed, which is 0. The average of the two times the time will give me the fall. Let's make this easy. It fell a total of 38.16 meters. The final real fast speed, relatively speaking, is 27.35. The real initial, I almost want to call it initial prime or put an R here for the real initial, which is 0, is this. This is 2. Let me give myself just a little bit more room. And that's t, and that's the one we got to find. Oh, we can do that. I mean, the rest is pretty simple algebra, you guys. And again, you have all the answers here, guys. See what we got here. We'll go here. Again, we have all this. You're just a click away from being able to go backwards and seeing what is written down here and what arguments are being made to get us these answers. So add these two together and divide by 2. Okay, you got me on that one. I think it's going to be, let me see here. It's going to be 13.675, something like that. Let me just make sure. I mean, 13.675. Let me kind of think about that. That's going to be 1.2, 1.35. Yeah, I'm going to stay with that. That's if you divide it by 2, and then you got t right here. T is going to be just do the algebra, guys, at that point. And again, the idea here, they didn't go there. They didn't go there asking us, by the way, what is the total flight time? What's going on here? You know, what is this? Well, that's kind of an interesting matter in its own right. But let's see. $38.16 divided by 13.675. Right? 38.16 divided by 13.675. 2.79 and some change. But not a whole lot. 2.7905 about. Yeah, I think my round off is a little different. I mean, it depends what you're using. Yeah, I mean, for some reason, I rounded it. I rounded it a little differently, but that's not substantial. This is it. This is it. Is there a little bit easier way you could have pulled this thing off? Yeah, I kind of did something elaborate, and I did it on purpose. I purposely wanted to use this and to use this. It's a little more challenging, but perhaps a little more of a gut feeling. However, couldn't you have just did something like this? V0 or VI or whatever. Maybe I should have used V0 on that one. This works too. You started at the very top. What happened at the very top? At the very top, this thing fell or got dropped, and it started at 0. V0 was equal to 0 meters per second, and it fell down to the very, very bottom and reached the speed of 27.35 meters per second. There's a lot going on here. Tell me how you want to do it. Well, subtract V0 on each side and divide G. Sounds good to me. That looks familiar. That looks a lot like all those things I was saying earlier. It wasn't like VF minus VI over A. Getting back, the more things change, the more they remain the same. This is the same thing, guys. This is 27.35. This is 9.8. Now, there have been different round-offs going on here. The answer is going to be slightly different. Off by maybe 1,000th. Off by maybe 5,000th, 1/200th. That's 0.5%. That's not going to be an issue.
I just, for the heck of it, I'd like to take a look at it. 27.35 divided by 9.8. I'm confident the answers I gave are good. Right? Did we say that? We said 20, yeah, we said 27.35 divided by 9.8. It's the same answer. It rounds up a little more. The first answer was, the first one I got was 2.7905 roughly. This is 2.7908 roughly. So one's the answers were basically 2.7905, first scenario, this right here. The second scenario is 2.7908, somewhere in that ballpark. You're literally off by 3/10,000ths. They're contradicting each other by 3/10,000ths. That's nothing. For our purposes, that's not an issue. That has to do with round-offs that have occurred and everything else. So, good ballpark look at what's going on here. And there's notice, I could have done this to find the time and do the algebra, or done this to find the time having done the algebra. You better know the algebra. You better know the mathematics. You better know the trigonometry if you want to succeed in physics. Even non-calculus-based physics, you need to know the algebra very well. And you need to know the trigonometry at a decent level. So you have to know the mathematics. It's the topics themselves aren't so bad if you got the mathematics under control. You can get yourself through it. Okay. All right. So that is the second problem I want to do. There's the third problem I'd like to discuss from topic 3. So let's go there. This one, and the one we're about to discuss, has two-dimensional motion, and there's an up and down going on. So that makes things a bit challenging. When there's the up and down going on, I cannot just plainly assume everything's going in one direction, because they simply are not all going in one direction. So let's see what we can do. When they all were going in one direction, it was very easy, and we called everything positive. When things are going up and down, the g has to be negative, and then all the mathematics proceeds with the assumption that g is negative. Very, very important. Okay, so let me third example problem from topic 3. I think it's problem 13 from there in the Serway book, right? So see how that all proceeds, guys. All right, well, 13, pretty short answer, a pretty good short answer on the whole topic. Let's, problem 13 from topic 3. There's more we do in person, guys, in the classes as well, but let's, on page, again, in the Serway book, 11th edition, page 75, problem number 13, found in topic 3. So topic 3, problem 13. A brick is thrown upward from the top of a building at an angle of 25 degrees to the horizontal and with an initial speed of 15 meters per second. If the brick is in flight for 3 seconds, how tall is the building? There's a lot there. And actually the mathematics get you out of it, if you know the correct equation to use, the mathematics will get you out of it very well, very conveniently, almost almost more simple than the subtlety of the problem. But yet, again, the mathematics conveys it. It's like a three or four line proof in some sense. Once again, a brick is thrown upward from the top of a building at an angle of 25 degrees to the horizontal and with an initial speed of 15 meters per second. If the brick is in flight for 3 seconds, how tall is the building? That means it's going to hit the ground. Well, here's our friend the building again. The brick is thrown 15 meters per second. Here's Vx of the initial. Here's Vy of the initial. Here's a 90-degree angle. We're told it's a 25. Here's a 90-degree angle, and it's a 25-degree angle right here. What will that angle be? Not that anybody cares, but it'd have to be 65. 65 plus 25 is 90, plus another 90 is the 180. Well, the 25 is what we need, and we're going to remember how do we resolve vectors. You've seen me do that in other videos, and you've seen me do that in person. It is a 3-second fall. How tall is the building? It's a fascinating question. How tall is the building? Probably looks worse than it did before. Let me at least keep some of the blue in there, I guess. Keep the H like this. There's the height, guys. And we've got this. We got this. Total height of H. How's this thing going to play out? I think it's going to play out right here. They're not asking you a whole lot. Just find the height of the building. They're telling you the flight time. So I guess you could find one of the kinematic equations. You can find one of the kinematic equations that is going to talk about time. 15 meters per second is the initial speed, raw speed as it comes out, muzzle velocity, so to speak. If it's fired out of some kind of cannon that fires bricks, let's say, or a person just threw it, the initial speed, the initial muzzle velocity, in a sense, is 15 meters per second. If the brick is in flight for a total of 3 seconds, how tall is the building? It's as easy as this, guys. I mean, without really further ado on this whole process, you got to realize what's what. The best way out of this, the height of the building is H. H is a positive number. The problem is, it is a problem or it's not a problem. Make sure you're interpreting things right. To me, of the kinematics that we know, this is probably the ticket out of it, because they give us everything we need except for D. Now we got to be careful. Who's what? Well, this is where you got to be really careful. Let's talk about vertical components and not worry about how far this thing gets fired out. We could talk about how far it gets fired out. They never asked us that, but we could talk about that as well, assuming there's no air resistance. Tell you what I'm going to do. You started up here, and this thing flew, and it came down here. Yeah, that's fine. That's all well and good. Guess there's a lot we could answer. How high did it go? You know, there's a lot we could say. How far? You know, what kind of range did it have? You know, nobody asked us any of that. Nobody asked us what was the height it attained, the maximum height it. What was the maximum height it attained? What was the maximum height that it attained? Call that small h if you want. What's the maximum height it attained, and what's the x that it attained, the range it attained? Nobody asked us what the maximum height attained was, and nobody asked us what the range was, but we're going to answer that too, just for the heck of it. For right now, let's figure out the height of the building. The height of the building is h. I agree with you. But this thing got fired up here. If it got fired up here, this is at height 0, and down here is height negative h. Probably the easiest way to do it. At least to find out how high this thing is. How high is h? This thing, you're not going to, what is the final height? We're going to call this, the best way to do this is call this y equals 0. Down here, this is y equals negative h. That's not conveniently written in most generic formulas. You got to visualize what's happening. I'm going to solve this equation, but I got to call d something. Well, yeah, well, let's talk about the vertical stuff. As far as the vertical stuff is concerned, you guys, as far as the vertical stuff is concerned, this thing started at a vertical height of 0. We're going to call this, we're going to call this y equals 0. Correct. We're going to call this y equals 0 and then proceed from there. If this is y equals 0, down here is negative h. So you're going to write it as negative h equals v0y. I want the y component, the initial y component, times t plus 1/2. I wrote g here because g can be interpreted in a lot of ways, but we're going to use g as a positive number, so it's got to be negative g. When things are going up and down, you got to use a negative. We talk more about this. I mean, for the people with whom I'm in person. This guy fell. It went down to a height of negative h. v0y, so let's see how we could do this. Vy is equal to v0y is equal to v sine theta is equal to v sine 25 degrees is equal to 15 meters per second times the sine of 25 degrees is equal to, whatever that's going to be. So we'll plug these in here, guys. We'll figure out where we're going to go with this. So let me, the way I wrote this, I was kind of, nothing wrong how I wrote this. I just kind of, I kind of assumed the problems were getting done. Students themselves were kind of looking at this and actually getting it to there. So if you got to here, again, it's just this negative h can be an issue for people. Don't let it be. Just call, if you wanted to call this place 0, you'd have to kind of, this thing right here would be written something like this. D equals d sub 0 plus VIT plus 1/2 AT squared. Well, the H, the way you'd kind of call it, if you're talking about a height, this would be H, this would be H sub 0, this would be VIT plus 1/2 AT squared. If the very bottom, you guys, is 0, and this is a height of, let's say, h. Let's say the height of the building is actually h. So I want it to hit the ground at 0, and the height of the building is h. Then I got this. I subtract. This is the height of the building. This is the height of the building. It's a positive number. Subtract a positive number on each side, or add the opposite of this positive number, which is a negative h on each side. So h is a positive number, so add a negative h on each side, and negative h becomes VIT plus 1/2 AT squared. negative h becomes VIT plus 1/2 negative g. Let's see what we got here. Forgive me, guys. Let me just kind of give a little bit more room, if I can. VIT plus negative g t squared like that. Okay, guys. Well, maybe that needed to be done. I mean, it's the way the formulas are usually presented, my friends, there's kind of an initial one that's present. We frequently blow off writing. I frequently blow off writing, hey, d sub 0. It's already 0 in a lot of cases. Sometimes it's not. In this case, it's not. The d sub 0 in this case is the h sub 0. The h sub 0 is the height of the building. It's a positive height h. We'll do the algebra with the positive height h, subtract the positive h on each side. Here you go. You got the negative h. This is where all of this came into play. When I got to here, guys, I didn't really care about the initial muzzle velocity. I cared about the y component of it. The one I really care about, yeah, the VI that we talk about is really the VI initial. And that is, it's the VI initial in the y direction, which we can call it V0y. I mean, there's so many subscripts up here, you can get dizzy from it. The bottom line is, this VY right here, my friends, this VY right here is really what's the strong thing here beginning, and it's brought down to 0. This Vy is V naught Y, the initial Vy, and this is, I won't say it's the final, it's sort of a final up here. You know, it's got a value up here, which is, there's some kind of a Vy value here that's equal to 0, and there's some kind of a Vy value here that's, you know, this is a final, some kind of final Vy when it actually, there's a y component final when it hits the ground. We know right here, if you go all the way across from height h, it's going to be 15 meters per second. Yeah, right here at the height of h. Down here, it's even faster. There's a Vy component, really strong, and there's an even bigger number than 15 down here. There's a lot to be said, guys. There's a lot to be said. They're not asking us a whole lot, so right now we're not going to worry a whole lot, but I wanted to at least show you where this came from. And where it came from is d equals d sub 0. D equals d sub 0 plus VIT plus 1/2 AT squared. And then, you know, d is h, d0 is h0. h0, hey, that's the height of the building. Subtract the height on each side, and you get this. The VIY is just, I'm just caring about things going up and down. And we've seen that in the past when I've made derivations of, hey, what is the flight time? How long does it take to get to the apex of the journey? Let's just consider y components of velocity and manipulate those y components of velocity to get the answer. What is the total flight time? Just double what the other one was because there's perfect symmetry. Here you can't do it because there's not perfect symmetry. There's perfect symmetry all the way to here. Then right here, it just comes all the way down. It's not like you fired from the ground and it landed on the ground. You fired it from a height h, and then it landed h below from where you fired it. It landed at negative h height. You fired it from a particular height, you can call it 0, and it landed h underneath that height. So if you arbitrarily call the top 0, the bottom is negative h. If you want to call the top, if you want to call the top, I don't want. There's this. I just don't want to enter that. If you want to call the very top, if you call the top, the buildings of 0 height. What do you mean? Well, yeah. Well, the buildings of 0 height, if the grounds of negative h height, from negative h to 0 is a height of h. If you started from a height h, the bottom here is 0. True, but and we did kind of say that you're starting from a height h0, which is capital H, and at the end of the day, you're going down to ground 0. So they're really, in reality, you are calling this height. You could call this height 0, but you got to call the height of something h below that negative h, or you can call h below that, call it 0, and call this guy h. If this guy's height capital H and this is 0, here's your 0 where it's going to fall to the ground, and here's the height of the building. If you subtract h on each side, my friends, you get the negative h. So you can interpret it, oh, wait a minute, okay, the bottom is negative h. You can interpret it as 0 or negative h, just be consistent with your mathematics. Watch out. Perhaps I'm saying too much on this, guys, but I just need to. There's a subtlety here. At the end of the day, this is what you're looking at. This is what you're looking at. This whole dynamic is what you're looking at. Now, this V0y, this V0y is the Vy that was initially present. The V0y is the Vy that was initially present in the triangle. Here's the master triangle of this whole thing, I guess, right? Doing this. And, here's your Vx, here's your Vy, and we call it V0y or VIY. You can call a lot of things, guys. Just be consistent when you're doing this. So you got what you have here. So this is what you have here, and you're basically solving this. Well, if you grind out the problem, and the formalities aren't the big deal. Can we get the answer? And that is, we got negative h here. This V0y was this entire song and dance getting us right to here. 15 sine 20, so this is 15 sine 25 degrees. Here's t. Here's a half. It's got to be a negative 1 point. It's got to be a negative 9.8. It's got to be a negative 9.8. Yeah, I mean, it's true. They at least, we can get out of the woods. They told us if the brick is in flight for 3 seconds, how tall is the building? If the brick is in flight for 3 seconds, that means the total flight time, my friends. That means from this launch all the way down to here. So we got negative h equals, here goes. I mean, and you grind this, guys, and like I said, I'll leave it for people to do this on their calculator. This works, it's true. I'm having this aversion for writing a negative, and I normally do, but sometimes you have to. It has to be there. And certainly in these instances, when it goes up and down, it has to be there. Okay, I mean, so it's a long dance, but you do this. I mean, it's easier done than said, guys. I just wanted to express the subtlety, I guess, of what the heck's going on with this. Well, you do this, you grind this, you solve for h. or at least the negative h, I mean, at the end of all that. So you say, 15 sine 25 degrees. You've got the calculator. Just make sure you get the job done. At the end of all this, look at it. Everything is filled in. On the right-hand side, everything is filled in. Everything is filled in, and it gives you what negative h is. That's a negative right here. Everything's filled in, grind it out. And you got negative h equals negative 25.1 meters. Multiply by negative 1 on each side. That is the height of the building. The height of the building. That's all that they asked. We're done. That's all that they asked. Period. Now, I'll tell you what. That's the height of the building. The height of the building. Remember now. That's the height of the building. All right. What is the range? How far did that thing go from the base of the building? Yeah, they didn't ask us that, but it's a good problem for us to know. It's good for us to know this stuff, guys. There's some subtlety in the actual discussion of this. So let's, well, we know how to do this, guys. I mean, we found this at the end of the day on all of this. We can utilize a lot. We can utilize a lot. You can't just say, 3 seconds. Half of it is where the apex is going. Half of it's where the apex is going to get reached for small h. We'll call small h. I ended up calling h the other thing. So I gotta be careful with my symbolism, guys. That's it. You know that. You guys know that. Okay, let me see what I can say here. X, I mean, there's a really easy way to get the x. X is v sub x times the total flight time. I've been using t. I know I usually write capital T. Here, let me write small t for the total flight time. Maybe I can do that. Maybe I shouldn't. I don't know. Whatever. It's the total flight time. Let me make it. Let me try to change it, and you watch it. Okay, just be careful. I'm going to say capital T is the total flight time. X is x. V sub x is v cosine theta. Total flight time is t. V cosine theta is 15 meters per second times the sine of 25 degrees. Not the sine, the cosine rather. Times 3 seconds. Times 3 seconds. That's all it is. Okay, it should go pretty smooth. Let me go 15 times the cosine. 15 times the cosine of 25 degrees, get an answer, then multiply by 3. Again, guys, I'm doing this completely cold. They didn't ask us to do this, but we can do it. 15 times the cosine of 25 degrees is this times 3. 40.784. I guess. Where do you want to go with this? But 40.784 meters from the base of the building. This is from the base of the building with height 20 from the base of a building whose height is 25.1 meters. The building is 25.1 meters in height. The building is 25.1 meters in height, and the brick hit on the ground. The brick hit on the ground from the base of the building at a distance of 40.784 meters. What is the maximum height attained? Kill a couple birds with one stone on that one. We already know the building is at a height of 25.1. The maximum height attained, huh? Number of ways you could do it. Let's find out how long it took to climb to the top. Does everybody agree that the time to climb to the top kind of think about this a little bit. Yeah. Does everybody agree that the time to climb to the top, we'll call it t, the small t, to climb to the top, is equal to the final velocity in the y direction. At the top, at the very, very top, the final velocity in the y direction, the final y component of velocity at the very top, the final y component of velocity at the very top is of magnitude 0, and the initial y component of velocity is v0y or viy, which is the v sine theta, and you will divide that by negative g, where g is a positive number. Is this true? Is vf equal to vi plus at? Yeah. Is vfy equal to v0y or viy? I'm just trying to stay consistent. I put a 0 in there somewhere. A naught, which means just the initial, but that's the same as the initial. So the vy could be v0y initially, could be viy. So I don't know, if you want to put the viy, if you're a little more comfortable with it, do it. That's what this is, and that could also be viy if you want. I mean, there's an alphabet soup here, guys. Just kind of watch it. So these guys are here, and this is it's a deceleration. At the very top, this guy's 0. This is v0y, or viy, whatever you want to call it. And, whatever it was, right? Well, this v0y, you guys, like I said, this v0y is v sine theta. This looks a lot like the stuff I used to do. Add a positive gt on each side. V sine theta. Now, you saw me do kinematics just like this, guys. V sine theta. When there's symmetry, you multiply by 2 on each side, and that's the total flight time. Yeah, symmetry is this. This right here is not symmetry. This is symmetry, not that. So you can't really multiply by 2. I can know that t is v sine theta over g. And that's the time it takes to get to the very top. V sine theta over g. Okay? This could just as easily have been this v0y could be viy. Okay. So you got this right here. Well, okay. V is 15. The sine of 25 is the sine of 25.
this is 15 sine 25 over g. That's all right. G's positive. Remember, I already accounted for the negative phenomenon by putting a negative right there. So that's okay. Treat g as positive, but when it's up and down, you better make a negative quantity associated with gravity. With acceleration due to gravity, a negative quantity has to be associated. So we took care of that. And the algebra yielded it. It came out this way, and these are all positive numbers. And this is what you got. At the end of the day, what is that? Well, that's how long it took to climb up there. So 15 sine 25 degrees divided by 9.8. 0.64686468. Oh, yeah, it's not the prettiest numbers, guys. Let me just write something down here then. 0.646865, let's say. 0.6468. 0.6468. I'll leave it like that. 0.64686 seconds. Okay, whatever. There's a longer number here. I might even leave my calculator with the longer answer when I'm doing this, just to make sure I'm within any kind of margins of error that are being asked. How long, they could ask you a question legitimately. How long does it take, once the brick is fired, for it to reach the apex of its arc? The apex of its journey in terms of height, how long does it take right after it's fired? I know it's 3 seconds for this thing to make the journey. The thing starts from a building that is 25.1 meters tall, and it lands 40.784 meters from the base of the building when it lands. It's a 3-second journey. Of that 3-second journey, how many seconds went into going to the very top of the apex? To the very top of the arc. Of those 3 seconds, about two-thirds of a second, of those 3 seconds, about 2/3 of a second went into climbing all the way to the top once you fired it from the top of a 25.1 meter building. At the end of 3 seconds, it lands 40.78 meters from the base of the building. They didn't ask us any of this in this problem. We were done with this problem 15, 20 minutes ago, potentially, right? But what if they did? Can we answer the question? That's the big thing. Can we answer these questions? So you got the answer here. This is the time it takes to get to the very top. What is the very top? Well, the very top is 25.1 meters plus however much it climbed. Let's find out how high it climbed from the top of the building, and then find out how high it is. We're going to find out how high it climbed from the top of the building, and then add the building's height, 25.1, to see what the total height is above the ground. What's the total height above the ground, small h, that this thing attained? Well, man, it's all there, to be honest with you. I mean, we got this. Let's leave as much as we can up here, guys. Again, I always keep forgetting that you can always go back. It's not like it's erased and it's gone. Try to think here, guys. Okay, so I got this. Let me just kind of, I might keep the more accurate one on here, but that's accurate enough. How high is that thing going? Well, let's call it H. H prime is this climb. From here we'll call that H prime. And we'll call the whole thing H. But we'll call this one H prime right here. So let's see how it climbed over there, you guys. So H prime is VIY or V0Y. I've been using V0Y all day. So V0Y times some t that it took to climb. And we know that t, it's over there on our far right. Plus 1/2 negative, plus 1/2 AT squared. And the A is negative G, the whole thing squared. How far of a climb is that? Well, I'm going to find out what the climb is. You know, guys, you all know, you all know, look at it right here. The H is going to be H prime plus the height of the building. Don't get caught up with the symbols, guys. Use your own symbols. Figure out what you're going to do. The H is going to be H prime plus the height of the building, which is 25.1. That's the total height above where it's at. So we'll cross that bridge when we need to. V0y is V sine 25 degrees times t plus 1/2 times a negative 9.8 times t squared. H prime is, it's going to be 15 sine 25 degrees times the t, which is this mess, 0.68, forgive me, 0.64686, 0.68, and of course I got it wrong, 0.64686. 0.64686. If I'd have gotten that wrong because of what I wrote, who's at fault? I am. I'm the guy who wrote it. Okay. It can be a fair exam, you guys, and you can get it wrong. If you got it wrong, I'm not the one taking the exam. Always tell people that, right? That's kind of obvious stuff. If you're the one driving a car and you get into a car accident and I'm the guy who taught you how to drive, well, unless I taught you wrong, right? But if I taught you right and you're the one driving the car and you got into the car, that's on you. I wasn't there. So we got this plus 1/2 plus, whatever, this whole thing. So let's kind of be rigorous about it. .64686 All right, that's what it is. Let's see where this thing's going to go, guys, I guess you could say. So, let me see, the hardest part is just grinding out the numbers, guys. So we did a lot. Let's just erase a few things. We can come back. We got some basic ideas of what we're doing here. Got a lot of data here. Some we can leave up there, some we don't have to leave up there. Okay. All right, guys. Rest is just the basics, guys. The stuff we know how to do. We got to be careful. There's got to be precision. We don't make a careless mistake. If we're the ones who make the careless mistake, it is obviously our fault. If somebody else makes the careless mistake, it is their fault. So this is on us right now. We got to get this thing right. Let's look at it.
15 sine 25 degrees times that number. So let me try to think here where I want to go with this. Might double check it as well. I'm going to leave it. I'm going to leave the numbers as they are. Let me just be careful here. I'll use the numbers I have up there actually, so we can all agree, I guess. 15 times the sine of 25 degrees. Sure, everything's right. Times 0.6466 times, and that the 1/2 times this is negative. Where are the signs here? Negative. Let me think, guys. Forgive me here on this one. Let me take this out of there. Plus. And I might want to double check this. I don't want to, be proficient with your calculator, guys. I mean, it's. Okay, guys, for some reason, it is doing something here. Okay, let me. Let's try it again. Okay, I don't know what's going on with this thing. Let's try it. Let me. Something I'm missing, but let's try this again, guys. Forgive me here. 15 times the sine of 25 degrees times 0.64686. 0.64686, got it. Enter. Plus tell you what I'm going to do. Since it's doing something odd, I am going to figure this out. You got to watch it with the calculators, guys. Okay, I think I got this. Sure didn't go too high, guys, according to this. Well, I'd like to verify, but I'm going to do this again, too, guys, just because the calculator was doing some weird stuff. But if I can't get the answer and the calculator is doing something weird, I've got to figure out another way to do it. I am responsible if I do it wrong. Like I said, guys, they got a lot here. So I go here, probably overkill on that one. I got this, and the grand total height above the ground is 25.1 plus 2.0503. That's the total height above the ground, plus 25.1. That's 27.15, thereabouts. yeah, I just, you know, I got a little bit of a of a scare. So this is, you know, I'm obviously it's not drawn to scale, you guys, but you know, I'm getting that for an answer. I'd like to give it one more look, to be honest with you, just to kind of make sure everything's okay. Let me just. So we said it was a 25 degree. Make sure the angles are right and everything else that we're talking about is right. 25-degree angle that it's being fired up from, and that's where I'm getting the sine. You know, that's where we're getting all this stuff, you guys. I mean, it's, you know, the Vx is V cosine 25 degrees. The Vy is V sine 25 degrees. So we know that. I mean, from the beginning of this endeavor, we knew that. So let's see what we have here, guys. I'm going to just do it one more time, just to kind of be sure. Sine 25 degrees times 0.64686. I'm going to subtract the 4.9 times 0.646, right? Correct. 0.64686. Yeah, good enough for me, guys. It's coming out just right. Okay, so, you know, this is the amount of height above the building in terms of altitude, you know, and how far away from the base of the building was this height attained? Well, multiply the horizontal component of velocity by the time it took to reach the apex, and that time is 0.64686, and that'll tell you how far over in the x direction it went to reach that height. There's a lot of things you can say. Guys, we were, you know, conceivably done about a half hour ago on this stuff. They didn't even ask us very much of this. But why not look at it a little more deeply for good practice? Hopefully it's good practice for us, okay? All right, that is about it. Thank you all for your time. Take care. Good luck to you.